Hi, this video will look at another example for beam deflection. This is a very unique one. It started at the same one we had last time. It's a simply supported beam, and there's a concentrated load right in the middle, 200 pounds. And this at both left and the right side is 12-inch. Okay. And in the last video, we're talking about where maximum deflection is and what the maximum slope is. So imagine if I were drawing this profile of this deflected beam, would be like that, and the maximum slope will be happened here, right? And now the problem has changed. This problem is going to be like this. You have a simply supported beam with 200 pounds in the middle, 12-inch and 12-inch. However, there is 12-inch here as well. So what would this beam profile look like after being deflected? It would be something like this, right? Oops, I'm gonna use the red, the black one. So this is gonna be the profile of this beam look like, right? Where you get maximum deflection here, and here, this remaining section will be, original shape is like this. Now it's just gonna be shoot straight up, it's a straight line, and this is also 12-inch. Okay, so this length is 12-inch. And then, however, this problem is asking us how much is this going to be? What's the deflection right here? Okay, so how do we solve a problem like this? We're going to use our theta max, which is the slope of the deflection, because we know the slope of the deflection is at this point, right? From the last problem, theta max, we already solved it, and we're using that formula taken from the book table. It's PL squared 16 EI, and we got the answer as 0.4, not 0.4, 4.8 times 10 to negative 3. That's the slope we have. Okay, so now if we know the slope, its slope is basically right here, and slope is rise over run, right? And now how do we solve it? We have to thinking about when the angle is very small, when theta is small, then we know the tangent of that angle is going to be equal to the angle itself in radians. So the slope is rise over run. Basically, it is the tangent of that right triangle. So then we are saying this slope here, 4.8 times 10 to negative 3, is going to equal to this angle right here, theta. Okay. I probably shouldn't use theta because here I'm using theta. I'm going to use alpha. This angle alpha. So that's going to be equal to this angle alpha in radians. So this is in radians. Then if you go ahead change this radians to degree, so this alpha is equal to 4.8 10 to negative 3, because this slope is equal to the angle itself in radians. So that since the slope is that value, so the angle is going to be this radians. We're going to change that to degree. How do we do that? We're going to divide by pi and times 180, right? So let's put into calculator, see what we got. 4.8 times 180, then divided by pi. And I have a value here. It's quite small. It's about 0.28, right? Because there's 10 to the negative 3 here. 0.28 degree. So this angle is super small, 0.28. And now we have to thinking about what will be the distance, how much is going to shoot up here. And how do we solve it, right? Then you're going to thinking about this question mark here. It's going to be equal to I'm going to do a different way. So this question mark over this hypotenuse 12-inch is going to be equal to sine of that angle, sine 0.28 degree. So in that situation, you can go ahead and solve your question mark. So it's 12 times sine 0.28 degree. That will give me an answer of 0.059 inches. So that shows me how much this end is going to go up. It's going to be equal to 0.059 inches. Okay, so let's quick recap on this problem. We actually use the beam deflection, the slope particularly for this one, and then we manipulate the geometry and to figure out this straight rigid line, what will be how much rise up. Okay, so that's all for this video, and I'll see you at the next one. Bye.